I'm Professor Barber. This video will explore the relationship between limits at infinity and horizontal asymptotes. Where might this concept and these skills be used? Market saturation analysis is a good example. Let's consider a new product is placed on the market and becomes very popular. Its quantity sold N is given as a function of time T, where T is measured in weeks. The saturation is modeled by the function N of T equals 250,000 T squared divided by the quantity 2T plus 1 squared for time greater than 0. What is the saturation level? What is the approximate point in time in which there is no longer a viable market for this product? Theorem. The limits of power functions at infinity. If P is a positive real number and K is any real number except 0, then we have the following four parts. A, the limit as x approaches negative infinity of some constant K divided by x raised to a power of P equals 0. And B, the limit as x approaches infinity of K over x to the P also equals 0. Both parts A and B tells us that if the absolute value of the denominator gets larger and larger, the whole expression will get closer and closer to 0. Think of slicing a pie. If you cut it into 2 slices, you have a substantial slice of pie. However, if you cut it into 10 slices, then a single slice would be a little bit thinner. And if you cut that same pie into 1,000 slices, a single slice would be so thin it would kind of be like getting nothing. That's the analysis here. Part C. The limit as x approaches negative infinity of k times x to the power of p can equal positive or negative infinity. And similarly, the limit as x approaches infinity of k times x to the power of p can equal positive or negative infinity. Both of these tell us that as you increase the power of x, the power function gets larger and larger. Pay close attention to the sign of the constant, which is the k value, and whether the exponent p is even or odd. Use both of those to determine whether your function is approaching positive or negative infinity. Find the following limits. A. The limit as x approaches negative infinity of 2 over x cubed. Regardless of whether the value in the denominator approaches positive or negative infinity, the absolute value is getting very large, and that means the entire expression will then approach 0. B. Find the limit as x approaches infinity of negative 6 divided by x to the 4th. Similar to the previous example, the denominator for this one also gets very large, and when that happens, the expression will approach 0. C. Find the limit as x approaches negative infinity of 3 times x squared. This is a power function, and the x approaches negative infinity. However, the x in this expression is squared, and the product of two negatives is squared. So as x approaches negative infinity, the x squared approaches positive infinity. And a value approaching positive infinity multiplied to the constant of 3 will still approach positive infinity. Let's continue and do some more. Part D. Find the limit as x approaches infinity of negative 8 times x cubed. As x approaches infinity, so does x cubed. Multiply that by negative 8, and we get that the limit as x approaches infinity of a negative number, that's negative 8 times x cubed, is going to be negative infinity. E. Find the limit as x approaches negative infinity of the expression 5 divided by x raised to the power of 3 halves. Let's write the x to the power of 3 halves as the square root of x cubed. Notice that x cubed is under the square root. Now let's think about that. As x approaches negative infinity and we cube it, that will be negative. However, we're taking the square root, and we cannot take the square root of a negative number. Therefore, the limit does not exist. Theorem. Limits of polynomial functions at infinity. If f of x equals a sub n x to the n plus any arbitrary polynomial function, then the limit as x goes to positive infinity of that polynomial function is going to be the limit as x goes to positive infinity of the leading term. That's the highest degree term of the polynomial, and that can be either positive or negative infinity. And the limit as x goes to negative infinity of that polynomial, p of x, is equal to the limit as x goes to negative infinity of the highest degree term of that polynomial, which can also be plus or minus infinity. Each limit will be either positive infinity or negative infinity, depending on the value of a sub n, that's the leading coefficient, and n, that's the degree of your polynomial. This theorem tells us that the extreme ends of a polynomial function, that is, as x either goes to the positive or goes to the negative of infinity, the graph will also approach positive or negative infinity. This represents the end behavior of the polynomial. The first describes the right end behavior, and the second describes the left end behavior. Give and evaluate a pair of limit expressions that describe the end behavior of the polynomial functions. A. G of x equals 3x to the fifth plus 2x squared minus 7x. This is a polynomial function of odd degree. That's because the highest power present is to the 5, and 5 is an odd number. And the leading coefficient is a positive number. The leading coefficient is the number 3, and it's positive. The right end behavior, that is, the limit as x goes to positive infinity of g of x, is going to be positive infinity. That is, the function is increasing to the right. The left end behavior, which is the limit as x goes to negative infinity of g of x, turns out to be negative infinity. That is, the function is decreasing to the left. B. F of x equals negative 4x to the fourth plus 7x minus 11. This is a polynomial function of even degree. It is an even degree because x to the fourth is the highest degree and 4 is an even number. The leading coefficient is a negative number. The leading coefficient is negative 4, and so that's negative. The right end behavior, that is, the limit as x approaches positive infinity of g of x, is going to be negative infinity. So the function is increasing to the right. Left end behavior, that is, what's the function doing when x gets real small? Limit as x approaches negative infinity of g of x is also negative infinity. That is, this function is decreasing to the left. Horizontal asymptotes. The figure on the right shows a graph with two horizontal asymptotes. As x approaches infinity, that means gets bigger and bigger, the graph approaches the horizontal line y equals 2. As x approaches negative infinity, that is, x gets smaller and smaller, the graph approaches the line y equals negative 2. In general, a horizontal asymptote is the line y equals b, where the limit as x goes to negative infinity of f of x equals b, or the limit as x approaches positive infinity of f of x equals b. Find the horizontal asymptotes of the following functions. H of x equals 2x to the fourth minus x cubed minus 9x plus 13 divided by 5x to the fourth minus 7x plus 6. We take the limit as x approaches infinity or negative infinity to find horizontal asymptote. To find the limit, let's factor out from both the numerator and the denominator separately the highest degree term. So, the numerator is 2x to the fourth times 1 minus 1 over 2x minus 9 over 2x cubed plus 13 over 2x to the fourth. For the denominator, we factor out 5x to the fourth. Then you still have 1 minus 7 over 5x cubed plus 6 over 5x to the fourth. Let's simplify. We notice that the x to the fourths cancel. So now we'll take the limit as x approaches infinity of 2/5 times, and then in the numerator, 1 minus 1 over 2x minus 9 over 2x cubed plus 13 over 2x to the fourth, and in the denominator, 1 minus 7 over 5x cubed plus 6 over 5x to the fourth. Now let's take the limit. The 2/5 stays put, and in the numerator, we will get 1 minus 0, because 1 over 2x and x going to infinity is 0. Similarly, minus another 0 plus 0. Let's look at the denominator. You will have 1 minus 0 again, because if you have 7 over 5x cubed and the x cubed gets real big, that entire term goes to 0. Similarly, plus 0. So that simplifies to 2/5. We see that the horizontal asymptote is y equals 2/5. Notice that the behavior of this rational function as x approaches infinity is determined by the ratio of the highest degree terms, the numerator and the denominator. B. G of x equals 5x cubed minus 6, all divided by x squared minus 4x plus 7. So, to find the horizontal asymptote, we'll take the limit of this expression as x approaches infinity. Seeing that we actually just evaluate only the highest degree terms, let's write the limit as x approaches infinity of 5x cubed minus 6 divided by x squared minus 4x plus 7 is the same thing as the limit as x approaches infinity of 5x cubed over x squared. And that simplifies to the limit as x approaches infinity of 5x. In this expression, when we let x approach infinity, the entire expression goes to infinity. Remember, if the limit approaches infinity or negative infinity, then the limit does not exist. And since the limit does not exist, there is no horizontal asymptote. C. F of x equals x squared minus 8x divided by x cubed plus x. Let's follow the methods of parts A and B. That is, find the limit as x approaches infinity of x squared minus 8 times x over x cubed plus x. This is equal to the limit as x approaches infinity of the ratios of the highest degree terms. In this case, it'll be the limit as x approaches infinity of x squared divided by x cubed, which simplifies to 1 over x. So we would write the limit as x approaches infinity of 1 over x. This is a rational expression. 1 is a constant in the numerator, and as x gets real big, the entire expression goes to 0. That is, the limit is 0. Therefore, the horizontal asymptote is y equals 0, which, by the way, is the x-axis. Theorem. Limits of rational functions at infinity and horizontal asymptotes of rational functions. This theorem will try to capsulize everything that we've done in the last previous examples. Part A reads, if f of x equals a polynomial function with a leading coefficient of a subscript m times x subscript m divided by a polynomial function of leading coefficient b subscript n x subscript n, then the limit as x approaches infinity of f of x is equal to the limit as x approaches infinity of the ratio of the leading coefficients. Similarly, for limit as x approaches negative infinity, which is going to be the ratio of the leading coefficients. When this happens, there are 3 possible cases. 1, if m is less than n, that is, the degree of the numerator is less than the degree of the denominator, then as the limit approaches both positive and negative infinity, it all approaches 0. Then we get y equals 0, and the x-axis is the horizontal asymptote. If m equals n, that is the degree of the numerator equals the degree of the denominator. When we take the limit as x approaches positive or negative infinity, the resulting will be the ratio of the leading coefficients. So the horizontal line, y, which is equal to a sub n over b sub n, is the horizontal asymptote. And finally, if the degree of the numerator is greater than the degree of the denominator, then each limit will either be positive or negative infinity, depending on the values of m, n, a sub n, and b sub n, and f of x will not have a horizontal limit. This affirms the results of the three previous examples. Part A, in which the degree of the numerator and the denominator were equal, the horizontal asymptote was the ratio of the coefficients of the highest degree terms. We got similar reaffirming results for parts B and C. Now, you have been presented with the skills and concepts needed to be able to solve the initial problem of this video, the market saturation problem. A new product is placed on the market and it becomes popular. Its quantity sold, noted by cap n, is given as a function of time t, where t is time measured in weeks. The function is n of t equals 250,000 t squared divided by 2t plus 1 quantity squared for time greater than 0. The questions are, what is the saturation level? You can solve this, and the way to do that is to find the limit as t approaches infinity. The saturation level would be the equation of the horizontal asymptote. And what is the approximate point in time in which there is no longer a viable market for this product? That is the approximate point in time. The question that's being asked is, after how many weeks will this product approach the horizontal asymptote? I think you can do this.